Today we're talking about trigonometry, specifically on right angle triangles. So let me zoom in. Okay, so we're talking about trigonometry and right angle triangles. Maybe you have learned this at school before, but let this just be a little bit of a recap, and as usual, stop me anytime it starts to get confusing, or if you start to lose me, or if I'm talking too quick, please just stop me at any time. Okay, so I'm gonna start off here by specifying what is exactly a right angle triangle. Okay, of course, as the name goes, it's a triangle with a right angle. Very simple in that sense, but it may be a little bit more tricky to spot when the triangles are rotated in such a way that you don't immediately recognize there to be a right angle. But as you can tell in the second triangle that I just drew, same thing. As long as we have a corner with a right angle, then still the both of these triangles are actually both right angle triangles. Okay. Now, especially in these right angle triangles, we have a very special rule. We call it the Pythagoras theorem. Do you recall this maybe? Okay, very good. It's got to do with a hypotenuse. Very, very good. Yes. So this Pythagoras theorem is very special to right angle triangles. This rule only exists in right angle triangles because of the existence of the hypotenuse. That's right. Okay, so hypotenuse being the longest side of the triangle, which of course is the side that is opposite to your right angle. Very good. Okay, now on this, I'm gonna draw a very rough sketch. Let me make this one. Okay, let's make this one 4 centimeters and let's make the other one 3. Okay, let's just use centimeters as units for now. But one thing is that I haven't actually specified all the units or all the measurements in this triangle, so there is actually one side that I did not specify, which as you can tell it's the diagonal side. There is something special, and this is where we are going to implement what we were reciting just now about Pythagoras theorem. Let me just help you out here by drawing out the right angle in this exact triangle. So at the bottom corner you can see the right angle there, and we were saying that the side that is opposite to the right angle, that is actually going to be the longest side of a triangle. So not 4, not 3, has to be the side that is opposite of the right angle, and we call this side to be the hypotenuse. Okay, now can you help me out here to recite the equation of a hypotenuse in a right angle triangle? Okay, good. So something about c squared, very good. Do you remember now what actually makes up the c squared? So that if the hypotenuse is c squared, what exactly is c squared made out of? Good, a squared plus b squared. There we go. C squared is definitely the hypotenuse, or c is the hypotenuse, so that c squared is hypotenuse squared. But what exactly is a and b? Okay, so a and b are the other two sides, but which one is 3 and which one is 4? Will a be 3 or will b be 3? Okay, so you can choose a as 3, that's good, you can do that, but actually there is no rule as to what should be a or b. As long as you have a and b to be the two sides that are not the hypotenuse, I repeat, any two sides that are not the hypotenuse, so 4 and 3, it really doesn't matter if you're going to specify a to be 3 and b to be 4, or if you're going to do it the other way around, you will still get the same answer for the hypotenuse. So again, it doesn't really matter, you can use a and b interchangeably as long as the hypotenuse, or the longest side of a triangle, remains to be c. Alright, now knowing that, can you help me to specify the working to find the hypotenuse in this exact triangle? Okay, so we have 4 and 3 as measurements. Okay, good. So we're looking for c squared, you're right. Okay, Very good. So to find c squared, we're going to use the sides 4 and 3. Let me zoom in. Okay, so to find c squared, we're going to do 4 squared, or 16, and 3 squared as 9. And that will, let me just write that down as 16 plus by 9, which gives us actually 25, which is still c squared. Okay, so is the hypotenuse 25 then? Okay, not quite 25 exactly, because it is still c squared, and we did say the hypotenuse is c, not c squared. So actually, yes, the hypotenuse would be 5, which comes from the root of 25. Okay, now up until this point, I want to ask you a question. The root of any number, usually we always give the positive and negative values. So why do we assume just now, why did we assume that the hypotenuse is positive 5 centimeters? Why not negative? Okay, so do you think you've ever heard of something being measured to be negative 5 centimeters or negative 100 centimeters? No, right? So specifically for length, although we are taking the square root of c squared, we are only going to take the positive value, which is 5 centimeters, as you can see there. We're not going to take the negative value because it does not make sense to have negative 5 centimeters as the length of c. Okay, till here, does that make sense? Okay, very good. So this kind of sums it up for Pythagoras' theorem. So hopefully it's all clear now. Again, if any part of this is confusing, please feel free to stop me at any time. But let's keep going now. For now, I'm actually going to bring over this rule up to the top there so that you can have it really easily during your revision. Alright, so Pythagoras' theorem, c squared equals a squared plus b squared. C is the hypotenuse. That's the most important part. Hypotenuse, okay, is going to be c. Very good. Okay, let's keep going now. Now, there is another special rule for right-angled triangles that is not Pythagoras' theorem, but maybe can you recall some sort of abbreviation that we work with for right-angled triangles? You're right, it's got to do with the length of something and the angles. Sine, that's right. Okay, can you maybe elaborate or specify the rule that you are describing right now? Okay, so a over sine A is equals to b. Okay, b over sine b, good. Okay, so although this rule can still be applied in right-angled triangles, this is not the one that I am looking for exactly. Again, you can still use this rule, but this is not the abbreviation that I'm looking for exactly for now. So can you recall another abbreviation that involves sine, cosine, and tangent? Good, yes, that's it actually, that's right. So we're actually looking at the abbreviation SOHCAHTOA. There we go, SOHCAHTOA. Yes, that's it. So this abbreviation is going to help us to actually solve for missing values, whether it be lengths or angle measurements of a right-angled triangle. Now, the one that you were saying just now is correct, although this one is specific to right-angled triangles because of the existence of hypotenuse in these formulas, which of course for a non-right-angled triangles we don't have what we call a hypotenuse, or the longest side of a triangle. We cannot specify that if it's not a right-angled triangle. Okay, so on this, can you help me to elaborate? What exactly do these abbreviations actually stand for? So we have SOHCAHTOA, but what exactly do they stand for? Starting from so. Okay, so stands for, okay, yes, so the S is for sine, very good. And O opposite, and H hypotenuse. Okay, very good. So sine theta stands for opposite over hypotenuse. What about cosine or ca? Okay, good. Cosine theta is adjacent over hypotenuse. That's very well done. Let's do the last one, tangent. Okay, tangent is opposite over Adjacent. Very good. So you're recalling all of these. That's a very good sign. From these identities or from the SOHCAHTOA abbreviation, we can actually again solve for missing values. And I'm just gonna bring down this example here so we don't have to work with another triangle. Okay, but I'm gonna pretend that we did not solve for hypotenuse, so we don't know the 5 centimeters. Forget about that. Say we did not solve for that. But I want you to use 4 centimeters and 3 centimeters to solve for this theta. So that theta is a missing value that I want you to solve for. Any ideas now? How are we going to solve for theta? Okay, good. Using sine. Okay, so sine theta is equals to, from the above, opposite, which is, there we go, opposite of theta is 4. Hypotenuse. Okay, there we go. So now we have a missing value. Although yes, we did solve for hypotenuse just now, it was 5, but we're going to pretend we did not know that. So we actually have 2 missing values. We have theta and hypotenuse to be missing, so we can't be using sine. We have 2 incomplete information. Therefore, sine theta or so may not be the most appropriate tool to solve for theta here. Okay, let's consider this. We have theta, we have the opposite, which is 4, and we also have 3. So 3 is actually adjacent to theta. 3 is the side that is beside the angle theta that is not the hypotenuse. Again, what we call adjacent is actually the side that is beside of the angle, right beside, but not the hypotenuse, the other one, which is, in this case, 3. So we have opposite, we have adjacent. Any ideas which one of these identities may be the most appropriate? Okay. Yes, I agree. I think the most appropriate identity to be using in this case is tangent. So tangent theta will be, again, following from the above, opposite is 4, over adjacent is 3. There we go. So, is that it? So, is theta 4 over 3? Okay, good. Not quite exactly 4 over 3 because that is tangent theta, not theta. So how exactly do we solve for theta then? Okay, so we're actually going to solve for theta by doing inverse of tangent and putting in brackets 4 over 3. Okay, can I see your calculator right now? Just to make sure. Okay, yeah. So, for your calculator, you are gonna have to click on shift and tangent. Can you see a tangent inverse coming up like a tan with a power -1? Okay, yeah, perfect. So when you have that, you're gonna punch in 4 over 3 and then don't forget to close in brackets. So as you can see in my calculator, it's like tangent inverse 4 over 3 and I closed the bracket there. Yes, okay. So can you punch that in and tell me your answer? Okay. Alright, so this should be equal to 53. 2 significant figures would be good. Okay, yeah, 53.1. There we go. 53.1 degrees, that's right. So that actually gives us the measurement for theta using SOHCAHTOA, specifically using TOA in this case. Now question, can we also use SOHCAHTOA to find the length? We can, yes. So say we know theta now, it's 53.1. Okay, I'm gonna keep it to 4 decimal points because we are using it as a working, so I'm gonna use the exact value. So 53.1301 degrees, that's theta. Okay, you said tangent, let's try that. Actually, let me name this x first so that we can easily identify what we are looking for. So let's name the hypotenuse as x. Okay, so you suggested that we use tangent to find x. Let's try that out now. So tangent of, again, I'm going to use the exact value or closer to the exact value. And that should be equal to tangent TOA is opposite over, okay, opposite over adjacent. Now, tangent 53.1301 should give you an exact number, which is 4 over 3. So have we solved anything by writing this down? Okay, we did not solve anything. We have just proven that tangent 53.1301 is indeed 4 over 3, but it has not really helped us to solve for x. So you are right, yes, we need to include x in our equation. Okay, cosine. Let's try that. So cosine, I'm going to use the exact value again, 53.1301 is equals to, cosine is CAH or CAH, which is adjacent. Adjacent is 3, okay? Over, there we go, hypotenuse is x. Now we have a missing value and we can work with this. Cosine 53.1301 is just a number, and I'm just gonna make this into a fraction form because on the right side we have a fraction so that it's easier for us to work with algebraically after this. I'm gonna make that over 1 because cosine 53.1301 is the same thing as cosine 53.1301 divided by 1. Cross multiplying that, we have x times cosine 53 is equals to 3 times 1, which is 3. Good. So x is equals to 3 divided by, yes, cosine of the angle. Very good. So I'm gonna try to use your answer function on your calculator so that you can get an exact answer. Now, as you're writing this on your calculator, I want you to be careful to put in the cosine in brackets so that your calculator does not get confused. What are we counting for? So make sure that you put in two brackets if you're using a fraction form in your calculator. If you're using divide, you're good to go. That's fine. Right, if you give exact value, you should give you 5, which we have proven just now with Pythagoras' theorem that x is indeed 5. Okay, let's keep going with the practice question here. So you have a regular pentagon, the bottom there. The previous question, the part question is up here. So each side of the pentagon is 10 centimeters. So AB is 10, and so is BC, and of course so are all the other sides. So they're all 10 centimeters along the base of the pyramid there. So I know this because it says regular. So a regular pentagon is one that whose sides are all the same, which in this case is given to be 10 centimeters. We were also given that all the sloping edges are 18, so I'm just going to write that down. Okay, now, looking at this 3D shape, can you help me to identify the name of a 2D shape, a triangle, a 2D shape that could help us figure out what is VO? So we're looking for a 2D shape. Okay, good, good. So we are actually looking for a 2D triangle, which we're gonna name a VO. So that's actually the triangle that's in the dotted line over there. It's on the dotted line, and I'm gonna mark the diagonal to be 18. Okay, other than 18, can you identify any other lengths that we can note down in our 2D shape from the 3D? Okay, so AB, BC, they're all 10 centimeters. AB is not in our diagram, but AO is. So if that's 10 centimeters and BC is also 10 centimeters, any ideas how we can get AO? Okay, good. So AO is actually an isosceles, part of the isosceles triangle. And okay, let's just say AO is Y for now. Let's keep it as Y. So when we've already found it, let's keep it as Y for now. Yes, I'm also gonna very quickly mark the right angle there so that's angle O, or corner of the triangle. Now, using Pythagoras' theorem, very good. We're gonna use Pythagoras' theorem to find VO. So VO squared is equals to 18 squared plus Y squared. Is that right? Okay, good thinking. It shouldn't be that way. Why not? Because from the previous Pythagoras theorem, we were saying C has to be hypotenuse. Very good. And of course, VO is not the hypotenuse. Therefore, we are actually going to switch over, make 18 to be the hypotenuse. 18 squared is equals to VO squared plus Y squared. Once you have found Y squared later on, then you can very easily find VO squared. Okay, very good thinking, very good catch there. Right, so it's important that we note that not all triangles will look like the regular right angle triangle in the same direction that we usually draw. Some of them may be rotated like in the way you see AVO to be here. Just remember how we're going to identify it is the opposite to the right angle, the side opposite to the right angle. That's where we have our hypotenuse. I will wrap it up there for right angle triangles, but next lesson we're going to be talking about non-right angle triangles.